Continuing our previous discussion on the core principles in RF microelectronics. In the previous section, we talked about power levels and ways to represent power. We looked at how we use the decibel scale to represent, to represent ratios, right? And we also looked at a new unit of power, which was dBm, as opposed to watts, which is the SI unit of power. So we now have two different ways to represent power, and the reason we choose dBm is because it helps us deal with the scale of levels of power levels we encounter in RF microelectronics, and it helps us work with them easily. So now dBm and watts, they can be interchanged using this relation here. Now let's look at an example. For example, now this example deals with converting power to voltages, and I would like you to remember the result of this example. So now this example is about an amplifier which senses a sinusoidal signal. So there are some important things to notice. There's a sinusoidal signal, okay, and it delivers a power of 0 dBm to a load resistance of 50 ohms. Okay, now we know power is VI, and in simple terms is V squared by R, because I is V by R, right? So you have V squared by R. Now for a sinusoidal signal, this V would be for a sinusoidal signal, this V would be V peak to peak RMS squared by R. Okay, and now what we need is peak to peak voltage swing, and V peak to peak RMS is V peak to peak divided by 2√2. Now if you use this relation in this, you'll get power as V peak to peak squared by 8R. Now we know that this is equal to 0 dBm. This power is equal to 0 dBm, which is 1 milliwatt. So that's what's written here. Your V peak to peak squared by 8 RL is equal to 1 milliwatt, and RL is 50 ohms. Then your V peak to peak is 632 millivolts. So I want you to remember this number. For a 50 ohm system, 0 dBm represents a voltage swing of a peak to peak voltage swing of 632 millivolts. So this is an important number to remember. And now let's look at another example which can use this number. Okay, so now a GSM receiver receives now again the important part is a narrow band signal having a level of -100 dBm. If the front end amplifier provides a voltage gain of 15 dB, calculate the peak to peak voltage swing at the output of the amplifier. Okay, now we have an antenna and we have an amplifier, and then it delivers to a 50 ohm system, okay, a 50 ohm load. It has a gain of 15 dB. It senses minus. Okay, now you have a -100 dBm coming in, and there's a gain of 15 dB, and then you have, so this is your V out, basically your P out, but since we have to talk in terms of voltages, I'll just write V out, and there is V in. Now what is V in? So to understand Vin, we'll have to convert this minus 100 dBm in terms of voltages. So right now we saw that 0 dBm is 632 millivolts for a 50 ohm system, and that's exactly what we're talking about. This is a 50 ohm system. So 0 dBm is 632 millivolts. Now how can we convert this minus 100 dBm to voltage quantity? Now we remember that minus 100 dBm, let's look at the ratio. So let's call this V2. Okay, let's call this V2. Okay, so that it falls in line with this. So 100 dBm is 100 dBs less than 0 dBm. So 100 dBs in terms of voltage quantities is 20 log now 632 millivolts divided by the quantity which we want to measure, right? Or if you switch this up, then it would be minus 100 dB. So I want you to look at this and understand where it comes from. Since minus 100 dBm is 100 dBs less, 100 dBs less than 0 dBm. So minus 100 dBm is 100 dBs less. So let's say 100 minus 100 dBm represents a voltage quantity V1. Oh, sorry. So let's say minus 100 dBm represents a voltage quantity V1, 0 dBm represents a voltage quantity V2. Then the ratio of these two would be 100 dB, right? So V2 would be 100 dB higher than V1. So that's exactly what we've written down. V2 by V1 would be 100 dBs, right? So when you write this and then you try to calculate V1 and you convert this 100 dB, this 100 dB would be 10 to the power 5 in absolute terms. So you have 20 log 632 millivolts by V1 is 10 to the power 5. Oh, sorry, 20 is 100 dB. Then when you divide this 20, you have log to the base 10, 632 millivolts by V1 equals 5. Then this 10 to the power, you take antilog, and then you have 632 millivolts by V1 is 10 to the power 5, which is exactly what's written here. So V2 is 632 millivolts. So then you can calculate V1. So V1 comes out to be 6.32 microvolts. Let me clear the screen so we can see things better. Okay, so now this is okay, so this is V in. What happened? Okay, yeah, so this is the amplifier. Oh, sorry, something wrong with the pointers. Let's just ignore this. Yeah. So you have minus 100 dBm coming in, and this is your V1, this is your V2. Sorry, this is your V out, this is your V in. And we saw that this minus 100 dBm, which is V in, it corresponds to a voltage of 6.32 microvolts. So just by remembering this number, this 632 millivolts, you can do some simple calculations and you can arrive at different voltage levels. So 6.32 microvolts at the input, and then the gain is 15 dB. If you convert this again to absolute values, it will comes out to be 5.62. So you can simply multiply these numbers, 6.32 microvolts times 5.62. So the output comes out to be 35.5 microvolts peak to peak. So you can use this number to simplify some calculations if you want. Another way to do this, which some of you might find easier, if you have a calculator you can do it quickly, is that you have a minus 100 dBm signal and you have a 15 dB gain. So you can simply add them and the output would be minus 85 dBm, right? Now you can convert this minus 85 dBm to watts, and then say it converts to x watts, then you can say VPP squared by 8 RL is equal to x. Then RL you know is 50. Then you can again calculate VPP from there. Involves a bit of maths, but if you remember these numbers, you can simply look at a table and you can get these values quickly. Okay, now let's look at some cases where the output voltage might be of interest. We said that we always try to look at RF power when looking at RF systems. But are there some cases where output voltage would be of interest? And the answer is yes. The first case is if different sections do not represent or do not follow a 50 ohm standard. For example, you have a system which is based on 50 ohms, and then you have the next system which is based on 75 ohms or 100 ohms. Then in that case you would be more interested in understanding the voltages at the interfaces and then converting them accordingly to the power levels for the next system. Similarly, if you have a capacitive input impedance, because capacitive or inductive impedances, they do not, you can't deliver power to them, they are storage elements. So if you have if you're looking at a capacitive, if you're looking at a capacitor, you cannot deliver power to it, right? You cannot deliver power to it. It's a storage element. So in that case you might want to look at the voltage swing which is happening at the capacitor. A more realistic example is in analog circuits, wherein you are driving the gate of a transistor, for example, and since the gate, the current is almost zero, so what you're driving is simply a capacitor. So you might want to understand what the voltage swing on the gate of a transistor is. Okay, let me clear the screen. Okay, now in the previous example, remember I mentioned this is an important point. You might also realize in the first example we talked about a sinusoidal signal, and that's why we were able to use this relationship, because you can write this relationship for a sinusoid, right? But if it's not a sinusoid, you can't really write this equation. It's not true for a non-sinusoid. But we use the same relation for a narrowband signal. And what a narrowband signal is that if you look at the frequency domain, you see that. So this is a narrowband signal. It covers a small range of frequencies, as opposed to a wideband signal, which covers a large range of frequencies. So narrowband signals, now the reason we were able to use that definition is because you can assume this, you can almost assume this to be an impulse in the frequency domain, in which an impulse in the frequency domain is nothing but a sinusoid. So you can assume this narrowband signal to be a sinusoid, but not always. I mean, for such simple calculations, you can assume them to be sinusoids. But if you're actually looking at modulation, you have to take the entire frequency component, the frequency, the composition of different frequencies. You have to take them into account. Okay. Now, this is a simple table which helps convert dBm to absolute power levels. Now, as we mentioned, the reference is 0 dBm, which is 1 milliwatts, and it might be helpful to remember some numbers. So 1 watt is 30 dBm, 40 dBm would be 10 watts. Okay. And 1 kilowatt is 60 dBm, 1 megawatt is 90 dBm, and 1 femtowatt is minus 120 dBm, 1 picowatt is minus 90 dBm. And now, if you open up your phone status, if you go to your settings and then look at the signal status, you'll find that your signal levels, your GSM signal levels, which are received by your phones, normally lie in this range. If you open up your phone, any Android phone, and well, I don't know how it works on iPhones, but for Android phones, you can just go to your settings and your signal strength. Normally there's an option where you can look at that, and the levels would be in this range. So if you convert them to absolute numbers, so the received signal, the received power by your smartphones is in the picowatts range, and then from the picowatts range, it is able to the internal circuits are able to amplify and then convert that signal into information. So that's, again, it's a pinnacle. Smartphones really are the pinnacle of modern technology. Being able to convert such small levels of signals into useful information is really amazing. Okay, so now, as you can see, we can go all the way from a femtowatt to a megawatt with just a few numbers, right? Minus 120 to 90, and you can cover the entire power range, the absolute levels. So all the way from 10 to the power minus 15 to 10 to the power 6. So this entire range is around 10 to the power 21. So you can cover this entire range of 10 to the power 21 watts by just 90 and 120 is, you can cover this. All of this can be covered using, this is 210 dBms. All of this can be covered in 210 dBms, right? So you start from minus 120 to 90 dBm, and you can get all the information in just a very small number. So that's the beauty of dBs and how log scale is used for power conversions. Now, another example to make things easier to understand. Now, let's look at power conversions from watts to dBms. Now, the power output transmitted from a cell phone is 30 dBm. At the receiver, the signal power received is 5 picowatts. What is the attenuation between the transmitter and the receiver? A very simple example. For example, you have a phone tower, you have a mobile phone tower, and then you have a smartphone, okay, or an older phone, a Nokia, okay, and then the signal is transmitting power and your phone is receiving some power, right? The oh, it's the other way around. Okay, so the phone is sending out a signal at 30 dBm, and the tower is receiving 5 picowatts. So the question is, what is the attenuation offered by the atmosphere in between? Now there are two ways to do this. One is you convert this dBm to watts and then you look at the ratio, right? You convert this to watts and then you look at the ratio in watts. The other way is you convert this to dBm and you subtract the two, right? That will give you in dBs. Let's do the first one. So okay, let's find the absolute power ratio first. So in that case, we convert this 30 dBm to watts, and we know that P P in dB is 10 log P2 by P1, right? So we have and in this case, if we want to convert 30 dBm to actual power, we know that 30 dBm is 10 log P2 by 1 milliwatt, right? That's how things are. Then you do this. Will, once you solve this, will come out to be P2 by 1 milliwatt is 10 to the power 3, right? And then if you calculate that, so P2 is 10 to the power 3 milliwatts, and P2 is just this number converted to power. So 30 dBm is 1000 milliwatts or 1 watt. This is the same number which we saw here. So 30 dBm is 1 watts. So you convert this 30 dBm, so this is 1 watts of power, and then when it goes through the atmosphere, it converts to 5 picowatts. Now you can simply calculate the ratio, the power received by power transmitted, and the ratio is 5 into 10 to the power 12. Okay, let me clear the screen. So this is the tower, this is the phone, for example, right? So 5 picowatts, this is 1 watt. So if this is P transmitted and this is P received, then the attenuation is P received by P transmitted, right? And it comes out to be 5 into 10 to the power minus 12. Now if I have to convert this into dBs, we know what we have to do. We have to do 20 log to the base 10 PR by PT, and if you do that, it comes out to be minus 113 dBs. So the atmosphere is acting as an attenuator of attenuation minus 113 dBs. The other way to do it is to convert 5 picowatts to dBms and then simply subtract. So if you convert 5 picowatts to dBms, it comes out to be minus 83, and minus 83. So you start with 30 dBm, right? So this is your phone. It transmits 30 dBm, and this is your tower. It receives minus 83 dBm. So what happens in between, right? So if this is your link, which is the atmosphere, say for example this is xdb, sorry, the ratio. If it's xdb, then 30 dBm minus xdb is equal to minus 83 dBm. So the attenuation would be, remember, the attenuation would be 83 plus 30, that is 113 dB. So this is the attenuation, right? And if you talk in terms of gain would be the negative, right? Again, in this case too, what we're looking at is the gain. So the gain is negative, which is equivalent to saying that the attenuation is 113 dBs, but the gain is minus 113 dBs. Again, you arrive at the same result, minus 113 dBs gain or 113 dBs attenuation. Okay. Now, can we use dBms at interfaces where there is there's no power transfer, like at the gates of transistors, as we mentioned previously, which have a capacitive input? There is no resistive input, so no power is delivered. But can you use dBm at those interfaces? And the answer is yes, you can. You can assume it to be a system which terminates in a 50 ohm load, and then you can always say that there is this many dBms of input power coming in, right? That's just to help you use these numbers when calculating something. For example, this voltage swing might result at the output might result in another voltage swing, which is another power level, which is another voltage level V2, which represents a power level P2, for example. So a power level P1 comes in, and although this power is not completely absorbed, it's converted to another power at the output, right? So you can take this as a black box and say that it converts P1 to P2, right? It converts P1 to P2, and in that case you can say that it absorb you can say that instead of talking about voltages, you can say that there's a power level of, say, P1 dBm at the input, there's a power level of P2 dBm at the output. So you can do that by simply assuming a 50 ohm termination at the input. Now, this topic is the issue of time variance as well as linearity. It's a topic which is easily confused, and it is sometimes interchanged, and people tend to confuse one for the other. And I would like to spend maybe another 15 or 20 minutes, but I see that we already spent half an hour on this. So in the next video, we'll talk about time variance, linearity, and the difference or the similarities between the two, and how seemingly some systems, seemingly they might look like they are time invariant, but they might be time variant, or they might look like they're non-linear, but they're actually linear. So we look at how to closely inspect systems. The same system in can behave non-linearly as well as linearly, depending on how you perceive it. We'll look at this in the next video. This is also something which is very important, which you need to understand uh, when dealing with RF systems. So see you in the next video then.